Okay. First of all, thank you very much for inviting me here in Estonia. It's nice to be here and see how much is being done. I will tell you about one project which we are leading at KTH. It's a 3U CubeSat project. This is outline of my talk. Briefly, I'll tell you about the objectives, why are we doing it, what we want to achieve, the concept. We look at the requirements, what exactly we want to do, that will be a bit technical, and I'll tell you where we are in the project. So this is an EU-funded project, FP7 cooperation, and it's actually funded in the SME part of FP7, small and medium enterprises. And we are the only non-SME partner in the consortium. KTH is a technical university in Sweden. It's the largest technical university in Scandinavia. And we are coordinating it. The rest of the partners that you can see here are small companies, well, except for SSC, it's Swedish Space Corporation. It's not very small, and it's actually a state-run company, but all the other companies are SME. And you will see here already GomSpace, which has been mentioned. It's a Danish company specializing in nanosatellites, but we also have ECM Space, which is a spin-off from TU Berlin, OAC Microtech, which is an Uppsala company making miniaturized electronics, Lenin, Ukraine, specializing in electromagnetic measurements, BLE, it's a small Hungarian electronics company, and Kaiser Italia, which is located near Pisa, and it's a small but very versatile space company. So what is it we want to do? Yeah, the overarching goal for the SME part of the space goal is the development of new solutions which will allow companies to reach the market, and we are obviously targeting the high end of the market. What do we want to do? We want to build a scientific CubeSat, which will be returning real science data. So in our case, we focus on the measurements of magnetic field, the DC magnetic field and AC magnetic fields. We will also use some new approaches for operation, and we will use high data rate, well, high compared to nanosatellites, of course. So this, the science goals can be summarized. Well, one thing we want to do is to look at the auroral currents, and that's something which we do research on at KTH. So my scientific research topic is aurora, and well, it's interesting starting from the monitoring of space weather, going into small scale, how the structure occurs in plasmas. That's what I work with. And of course, one satellite is not a big deal, but we will coordinate with other instruments, with SWORM mission, which has been launched last November. It's 3 satellites for precise measurement of magnetic field. Ground-based optics, which we operate on Svalbard, and our colleagues in Tromsø. IceCat radar, it's European coherent scatter radar, it's an atmospheric radar which allows to monitor the parameters of the atmosphere, and SuperGARN, which is a different sort of radar which allows to monitor drifts. So the second scientific point is we want to measure ELF and PLF waves in the sphere, well, actually the atmosphere, because we'll be in a low orbit. And those, well, the most pronounced ones are the ones which are generated by lightning strikes, and they're called whistlers, and they're very well known. The reason to look at them is that because if you invert the dispersion in relation to, you see the whistler here is a frequency change in tone as the wave propagates, so the lightning generates all the waves at the same time. And then as they propagate in the magnetosphere, they get dispersed according to their frequency, and looking at this dispersion allows to reconstruct the density profile in the plasmasphere, and that's an important parameter for space weather. Also, these waves are generated in the aurora, and if you look at some more exotic sources, people are talking about seismic sources of ELF and ELF waves, and so on. And the third topic is entrepreneurship. photogenic emissions, so emissions created by mankind activity, and these are power lines, signals and power line harmonics, which are sometimes observed is still poorly understood, but more data is needed. So, okay, this is in parentheses the Earth's field, of course, is constantly changing at a slow rate, and people work all the time to improve the IGRF models, which already been mentioned here in this audience. And to get there, you really need a slightly better measurement than we will achieve. But maybe on small scales, like looking at crossover fields, still things to be done in coordination as well. Yes, and the overarching long-term goal for us is distributed measurements in space. This has already been done. ESA cluster mission, which is a 4 satellites flying information in the magnetosphere, has been in space for 13 years, and it would have been in space even longer if the first launch on Ariane 5 succeeded, which it didn't, so it had to be revealed and launched on 2 Russian rockets. Anyhow, so we get data from there, we look there, and that's, it's important to be able to distinguish between spatial and temporal variations. On a satellite, we're looking at measurements along the orbit, and we, in many cases, are not sure whether it's a change in time or change in space. If you have many satellites, you can resolve it. NASA MMS, Atmospheric Multiscale, will be launched next year in the spring, I think. And we're also participating in this electric field instrument. That's also 4 satellites, but new generation compared to cluster. It will look at reconnection physics specifically. But we're also looking at doing it on smaller scales and in the hemisphere. So what we have been pursuing is doing mother-daughter type experiments with Rexus program, that's rocket experiments in Earth for students. And here in the picture you can see panoramic view from the rocket where 4 free flyers are injected, and these free flyers are fully spheres to analyze the atmospheric density profiles. So we had a couple of such successful experiments, and we actually got a real sounding rocket funded, which will be launched this winter. It's called Spider, where we look at characterization on multiple scales of particle Buoy instability in the atmosphere. And of course, the goal in the longer term is to do with nanosatellites, swarms of nanosatellites. But there are things to be resolved before we go there. So, the operation strategy. An important point you heard already a few times is that we can produce much more data than we can send down to Earth, and there are different approaches how to deal with it. You can compress data to some extent, you can schedule burst modes, you can make automatic burst criteria if you believe in those, or you can save all and then choose by a human operator what to download. And that's what we intend to do. We'll have multiple data streams saved on the satellite all the time, and the overview, a quick look at that downlink of each passage, or as often as appropriate, and then from those one can select what high resolution data you want. Yeah, that's what I said. So we record everything, and then get all the overview data down, and then select the high resolution intervals. And that's actually something we have been doing for 8 or 9 years already on Earth. We have an instrument on Svalbard, which is an island at 78 degrees latitude, so you can actually fly in there and work there, but it's still not very convenient. And we have our imaging instrument, and you can see with an arrow where it's located, so it's quite remote location. And the instrument is actually a set of 3 cameras, which can run at multiple frames per second and produce easily gigabytes of data very quickly. And it's not the same thing as on a satellite, but it's very similar. We have much more data. And what we do, we make quick looks, which you can see on online, and then an operator goes in and goes, okay, it was was cloudy, there was no activity, this we can delete, and then we can pick the data we want and work with it. So, yes, the second new approach we want to do is we want to use the commercial ground stations, because we will go into the S-band, and there you can actually work with commercial ground stations. And we'll primarily use S-range, but we'll also use the Azaraga station in Australia. And the vision is that if you want to go to commercial stations, you need to stick with the standards. There is something which is called CCSDS standard. It's quite ramified, but that's something we need to stick to. And also we want to automate the buses. So being a low priority and as a CubeSat, we can get the buses cheaper if we can allow to skip a bus or maybe take one later. And that allows the operators to improve the usage of the antennas, and it allows us to get the downlink time cheaper. Yeah, the orbit will be a synchronous orbit at 9:21 local time, 600 kilometers. So now I can quickly walk you through requirements. We are aiming at a lifetime of 1 year. We want a polar orbit or high inclination orbit across the Ural zone, and we want to measure the DC field with good enough accuracy. If you are into that, you will understand what it means. The same with AC field with the surgical magnetometer, and we want to keep the satellite-generated noise below the instrument noise. We need to know the position and the timing to be able to relate it to other data sets, and as I already mentioned, high resolution data is collected all the time, and then some intervals that are requested by human. Where we are now, we started about a year ago, so we had PDR in the spring, and we're working to CDR in next spring, and the launch is sometime in 2016. It's still not, we still have no contract signed. So the system overview, you can see color-coded who is making what, so you can actually see it's quite a collaborative project. We have all the science payloads here made by Leonie to some part by KTH, and they go into digital processing unit, which has a lot of memory, so that's the one which keeps the circular buffer. And then we have a computer actually taking care of all the support systems. You see this light blue comes from NoSpace, so that's their developments. And we have a TCM, which is a module of mass memory and the modulation, so that's the one which does the CCSDS standards. It's made by OAC Microtech in Uppsala, and then it goes into S-band full duplex transceiver, which allows to work with CCSDS standards. Yeah, this is a schematic how it will look like. So we have one view of NoSpace platform support. And we have all the fancy looking things on the other end, which are the payload and the DBU and the mass memory and the transceiver. We need to have deployable solar panels, and we also need to have deployable booms. So deployable boom is another feature here. We need to bring the sensor as far away from satellite as possible, which in this case means about a meter in each direction. And we also have deployable solar panels because we need some extra power. This is more or less a sketch of the mechanical solution we're looking at. It's heavily based on the ICE standard structure, but when we realized that mounting our non-standard system there would mean a lot of brackets and things, so we decided to make our own, which sort of starts from ICE structure but has some other mounting applications. Yeah, so that's what I have to say about this project. And in short, we are developing, we will fly a scientific studio CubeSat, and there are several technological developments, which is magnetic linearness. Of course, I haven't mentioned that it's very important to get good measurements and also to get good attitude. The deployable boom also helps us with gravity gradients and S-band telemetry with CCTS data structure using commercial ground networks. And the next step, sometime in the future, is of course fleet of CubeSat building on this concept. Yeah. Thank you.
Thank you. Question?
Thank you. One question is about these booms. So, what kind of booms are you going to use, and will you pay attention also to the magnetic effects that we here have trouble with?
Yes, of course. Magnetic cleanliness is very important. So we have a budget for magnetic moment, and we will also have two sets of coils. One set will be used for control, and the other set will use controllable current to compensate the residual magnetic moment to whatever extent we can. The boom is development at KTH. It was a joint development with Air Force Research Lab in New Mexico and in a different project, but now we have taken it and carried it further. It's based on a bistable composite structure. So it's fiberglass composite, which is bistable, so it unrolls like a little bit like a tape measuring spring, but in a controlled way. Yeah.
I have a question regarding commercial ground networks. What do you mean by that? You are looking for servers, or you are developing your commercial station?
We are not developing the station, but as I said, it's a consortium of partners, and one of the partners is SSC, Swedish Space Corporation. And the Swedish Space Corporation operates what is called PrioraNet, and this one of the networks already in existence. There is SSC's PrioraNet, there is KST, the Norwegian network, there are some American networks as well. And typically they have stations which have multiple antennas, multiple basebands, and they can provide services. In this project, they are providing it as part of the project, and also they're developing this semi-automated scheduling together with us. But once this exists, they will be able to provide it to other users, which stick to the CCSDS standard. And they are not interested in UHF. The lowest they give is the S-band. So we're looking at data rates of maybe 1.5 megabits per second on the downlink.
More question?
Question regarding the magnetic issues again. You're planning to do high precision measurements of the magnetic fields. Do you have exact models or precise models, or how are you planning to compensate for the residual magnetic effects of the satellite itself? And as you said, you're going to have a separate coils to compensate for that magnetic moment, but you can compensate for the magnetic moment control-wise, but it will still generate different magnetic field depending on the position where you are. So are you planning to develop a precise magnetic model at the point of each of the magnetometers, or how are you going to compensate for that?
The answer has like different layers. One layer is that we are trying to make the satellite as clean as possible. So we have a dedicated program of looking at the magnetic material content. So we eliminate ferromagnetics and soft magnetic materials. We had to change the batteries. We're looking like at each connector. We had to look through, screen about 40 connectors types to see what we can use and so on. But as it turns out, the requirement of the attitude is much more strict than the requirement on the magnetic field effects, especially for the DC. For the DC, if you're 1 meter away from the body, you can actually be quite dirty, and still you wouldn't notice it because it will be below the noise. But the attitude control we want to avoid controlling the attitude far too often. So we want to have periods of undisturbed dynamics where we still are in somehow controlled state. And that requires, that puts much higher requirements on the cleanliness. And that's primarily for that we want to compensate the moment. Of course, you can only compensate the hard magnetic component, and the soft component will do funny things. So still we need to keep it as clean as possible.
Okay, thank you, Mr. Yevchenko. And the next speaker is Vidmantas Tonkus from Lithuania Space Science and Technology Institute. Please, the floor is yours.
Hello for everybody. It's my pleasure to present also the next one, Lithuanian satellite results. And I would say that this was really challenging, as also Rinas told. Actually, both missions were organized mostly by the private initiative and not so much supported by the government. So the government has done already some decisions, but actually it was just actually at the end of the mission, and that the impact is that Lithuania, with some almost 3 years delay relatively to Estonia, is going to sign on October 7th the PEX agreement. So that's the good news for us. But actually the launching and the design of the satellites, it was really on the teams of the satellites. So I will explain a bit more about the second one satellite that was mostly managed by Kaunas University Technology and Space Science and Technology Institute. It's actually associated with Lithuanian Space Association. Both satellites were actually one unit, CubeSat, and they shared also some of the technology in means of power supply and communication model, but they had some different tasks and also some unique components. And LitSat, the main task of the LitSat was to look more about the measurement of the attitude, because for the next mission, Kaunas University Technology is going to test some university-made attitude and control components based on piezoelectrics. And it was quite important for us to understand how to measure and how to transmit data from the satellite back to the ground station. And we had also space-qualified GPS receiver on board, but it was not made by us. It was manufactured in Russia. And we had also linear transponder. It's a bit different to that was on Lithuania Sat, because it was a higher bandwidth and possibility to work for several radio materials at the same time. And we have been using also gallium arsenide solar panels. You see some of the pictures during the manufacturing process and how it was packed before the launch. The way of launching was the same. Actually, we had contract with Nanoracks, and thanks to the commercial initiative of United States companies, it went quite quickly, and they have supported us with all the tests, and it actually has been flown in the NASA cargo, and of course all the paperwork was much more easier than contacting directly. And I was trying actually to look at different ways, also both European, both American, or even Chinese. But this way it was, I would say, most cost-effective and more simple. So it's maybe good advertising for the Nanoracks company, because they're expanding and now they're cooperating with the company Skybox Imaging that actually has got financing several hundreds of millions for the launch of the small satellite on Planet Labs. So The satellite was brought to the International Space Station on the 12th January of 2014, and approximately in 1 month, with some delay, it was launched into the space on the 28th of February by the Japanese astronaut Koichi Wakata. And you see the same pictures how the 5 actually satellites from the same launch bay are flying in space. The ground station, we had using 2 ground stations. One was on the satellite teleport near Vilnius, in a village called Liepiškės. It's used for mostly for commercial communication, for internet background connectivity. And the second one station was installed also on the roof of the Kaunas Municipal Technology. So we had the possibility to do reception on both stations. But I would like now to focus more on the results. And actually, as we are looking more about the attitude measurement and control, so it was a unique situation that we can actually to compare several satellites launched at the same time and actually at the same speed, and to look how they behave. And as you can see in the bay, we have here 5 satellites, starting with Lithuania-Sat, LitSat, SkyCube, AutoSat, and Peruvian satellite UAPC-SAT. 3 of them are 1 unit, and we'll come back. And 2 of them are 2 unit. But it's quite interesting that they had very different behavior. And that's what we are looking now and trying to understand, to compare our measurements that we have got from the satellite, and also adapt this experimental data to our model. So as you can see, 2 of the satellites went down quite quickly, and that we are actually Peruvian, UAPC-SAT and LitSat 1. It took just less than 3 months. They launched let's say the 1st of March, and already at May 21st, 23, they went down. And it was a bit surprising for us, but maybe it's a good lesson, and we can use this knowledge for our next mission. So AutoSat went down on July 1st, so approximately a bit more than 1 month, and Lithuania-Sat on July 28th. So that means the construction was quite similar, but the difference is almost 2 months. And SkyCube is still in the orbit, quite high, 330 kilometers. The launch was approximately 411, as I remember. So the behavior it's really different. And now we are looking at the data and trying to understand what was actually the reasons here for that. Maybe I have to mention also that 2 of these satellites were 2 units, and SkyCube was interesting that actually it was 1 unit satellite, but the solar panels were deployed, and actually it became even I would say 3 unit satellite, because they were deployed and the structure was 30 centimeter long over 10 by 10 centimeter. So we are now looking at the data. We have got, I will show just a couple of examples, and then the model we are working with. So we had on board different sensors like a magnetometer, gyro, accelerometers. We had also photosensors on each of the solar panel, and of course also different telemetry from the EPS, so we can also look what was happening, how the solar panels were charging the batteries, so we can get also some information from that. And I put some examples. It was the moment of the deployment of the antennas, and you can see how the data of the magnetometer, but also of other sensors have been changed during the moment of the deployment of antennas. It was actually the impact. So here you see the magnetic sensor data. Here you can see the photosensor data. So actually also the orientation of the satellite was changed. And the gyro data, especially, you can see on the gyroscope how the satellite attitude was changing during the moment of deployment. Here are some some data how it looks like, how when the sunlight was irradiated by the sun. It comes from the shadow to the sunshine, and you can see like a sunrise from the satellite. But most interesting maybe are the data, the final data. We got the last data on the 21st of May, and actually on the 23rd of May, the satellite was deorbited. And we're looking mostly at these data because actually they have been measured at quite a low altitude, below 250 kilometers approximately, and that's one of the most interesting when you have different factors like aerodynamic drag. It was also a combination with some gravitational momentum and also of course some influence also from the magnetic material. Just here's some data about the accelerometers. Maybe are not so much interesting, just maybe can be used in combination with some other. The temperature, nothing maybe very new. It was changing between the +5 degrees up to -22, as I see. And more interesting are humidity data and gyro data. Of course, you see this bars because they have been measured just during the reception of the signal, and we had quite a short bypass, but we had the rotation of the satellite with a period of approximately 18 seconds. I mean, one rotation, one revolution in 18 seconds, and when the satellite was approaching the Earth, actually this rotation was increasing, and we actually got quite interesting and complex results on how different torques of the satellite have impact on the satellite attitude. And normally, as you are on the high altitude, then of course you can rely on different magnetic systems, but on the altitudes below 250 to 200 kilometers, especially if it will be the case of 350 and not so much aware how what will be the altitude of the launch of these satellites. I think it's very important to take care about all these factors. So actually, as you can see, this especially this one direction is a green line. So the number of the revolution was increasing during the last date, and it was reached almost one revolution per second. And I was listening also about the presentation, about the discussion of SQ, and it would be also very interesting to compare what data you're getting now and what is the configuration of SQ satellite, and also to look maybe and to try to compare to model wheel, looking now to combine all this data. Actually, initially the approach, of course, it was quite similar and standard. So you're looking at aerodynamic torque, about the gravitational orientation, and trying to compare how much of the impact of the delta V, of the loss of the delta V, is changing the altitude, the height of the satellite over the Earth. And looking, of course, also at the magnetic impact. But what we have got, now that's different. Got an estimating also ballistic coefficients. But what I would like to say that according to our measurements, the satellite was rolling over the plane of the big 2-meter antennas. And actually, at this altitude, I believe the orientation of the satellite is determined mostly by the both aerodynamic drag and also gravitational orientation, because 2-meter antennas, they are quite long, and they are about 60 centimeters. They are 2 antennas perpendicular. And these 2 torques, they are working on the attitude of the satellite. And at the same time, I believe it's also affected by the magnetic field of the Earth, and it becomes also, it has impact on the rotation of the satellite. So the data for the moment, this model is still not finished, but we are trying to compare and to estimate the parameters of the ballistic coefficient, of the aerodynamic coefficient, and look which one curve it corresponds best to the behavior of the satellite. And we'll try also to compare the other satellites that have been launched at the same time, like Lithuania, SkyCube, and Argosat. And we expect that most comprehensive, most detailed results will be presented approximately in 1 month in the KeySat workshop in Switzerland. And so, conclusions would be that we have found that the aerodynamic drag is not only a factor that is determining the decay of the satellite. Probably there are some other forces. We think that this rotation could dissipate also some energy on the magnetic hysteresis or the magnetic material of the satellite. And if you see this blue line and orange line, so actually this difference, we think, we're trying now to be more sure on that it's a result of the dissipation of the magnetic material. I mean, that some energy goes like a trolley bus, some dissipated in electric way. And we will also to compare this model with the other satellites and think that it could bring us better understanding for the next mission, especially if the mission would be with the goal of precision attitude control. So we need to have all this data and to use it during the design of our next mission. So thank you very much.
Thank you, Mr. Frankos. Please, your questions to the presenter.
Thank you for this very interesting presentation. I have not exactly a question about the presentation, but about one picture. How did they manage to get this burning up of the satellite on that telescope image?
You mean this? I believe it was just taken somewhere from the internet. I mean this one, yeah.
Yeah.
No, it's actually. Well, yeah, sorry, it's not our picture.
It says actually.
Yeah, but it's okay, yeah. Like Sandra Bullock, on the gravitation.
This is maybe not a question, but a comment. Could you show this sky? What was the name? SkyCube picture. Yes. So it's really So the interesting thing is that the SkyCube seems to. It remains in orbit for so long.
Yes, it's also interesting for me because it's 3 units and actually it has this deployable solar panel.
So could it be possible that there is some outgassing involved, so that there is outgassing from all the surfaces, and then this shape forms like a effective nozzle, so that this outgassing.
Like that, it's proportional.
So that if you outgas maybe 1% of the satellite, it might produce some centimeters of a second of delta V, which preferentially in one direction, but for these other satellites, perhaps this outgassing is isotropic, and therefore it does not contribute to this orbit. Just a thought.
Interesting approach.
Thank you. So, thank you. The last question.
Sorry, did you try to find out whether the deployment of the SkyCube actually occurred? Maybe they did not deploy, and that's why the coefficient is small.
Actually, we're looking just on our model, and we just are collecting all the data from other satellites. So I'm not sure I have seen that the plan was to deploy it, but I have to check, of course, the masses, the ballistic coefficients, probably what was the passive orientation, or how much of the magnetic material was inside. So it would be very interesting for us to compare. What was actually the reason? Maybe also some other reasons, like outgassing, I don't know.
Okay, thank you, Mr. Tonkos. As the next speaker, I would like to invite Mr. Lepinen, Aalto University.
Yes, thank you for the introduction. Good afternoon, everyone. My name is Hannu Leppinen. I work as a doctoral student at Aalto University in the eyesight project. So I will talk to you today about the onboard computer development from a system engineering point of view. So I hope I don't disappoint any low-level engineers here. My topic is how to combine easy access standards to a rapid development approach. I will first introduce a bit what is the eyesight project. We are happening in the media during the summer. I will also then discuss what kind of development practices we are using. And then I will use the OBC development as an example case. And I will finally present the conclusions. So, eyesight project. Currently there is a growing interest in the Arctic Ocean. Due to the global warming, the summer season is getting longer, so it's possible to operate more and more in the Arctic Ocean. So both shipping industry and the oil industry are expanding their operations in the Arctic. And to operate in the Arctic Ocean, you need to have accurate ice information. So our spin-off idea from Aalto University is to provide a constellation of microsatellites, 50-kilogram satellites, a total of 6 of them, to provide high refresh rate ice information with a synthetic aperture radar instrument. And where we are now, we have had long discussions with potential customers. I cannot name them, but we do know there's a business case for this idea. The design for the satellite has been frozen, and the subsystems are either nearing the engineering model phase, or either we have found a supplier for them. So we're going to acquire a lot of subsystems for the satellite. Our synthetic aperture radar is going to be developed in-house, and we are now currently testing it with our department plane. So it's attached to the side of the plane, and it's measuring some ground targets. Currently we're in the process of transitioning into a private company outside the university, and we hope to finish that by the end of the year. So next year there will be this eyesight company. And we're currently targeting to have a demo satellite by 2016. At our university, we currently have actually 3 satellite projects ongoing. So Aalto 1, Aalto 2, and eyesight. So we have been developing our own approach to manage these projects. When you do university space projects, you have 2 major problems. 1, you need to do high quality engineering, and 2, you have mostly student workforce who don't have that much skill, not that much time. So what we have been trying to do at Aalto is to learn from the best practices of the space industry, like ECSS standards, but also embrace methods from the Agile community. That way we can extract the maximum contribution from each student. But if we consider some systems too hard, we can outsource them. For example, in the Aalto 1 we have the attitude control system bought from outside. This approach has been used in the Aalto 1 and Aalto 2 missions. For ECSS, I think everyone knows it, especially after yesterday's lecture from Jan. It's the European Cooperation for Space Standardization. If you want to do business with European space operators, you have to know these standards. But if you really are going to follow them, it takes a lot of effort, even just to do the documentation. But on the other hand, these standards are written by the guys who really know how to do stuff. So it's worth going through them, even if you don't use them. I put the waterfall model there because that's something that usually doesn't fit well into a fast-paced CubeSat project, for example. So what we are doing at eyesight, of course, we spring from the Aalto 1, Aalto 2 heritage, so we use a lot of those methods. We used Aalto 1 and Aalto 2 as screening tests for valuable contributors. So we recruited the best guys to be part of the effort. And in ISI we have no educational objectives, so we actually outsource everything we can. The onboard computer is an exception because we did do a market study, but we didn't find a perfectly fitting solution. So we decided to do the design ourselves for this case. When you start to outsource stuff, you need to know ECSS, and also your own systems need to be ECSS compatible. For example, when we are developing the onboard computer, we need to know well this ECSS E7041A, which describes the telecommand telemetry utilization. So how the onboard computer should execute commands and respond to them. So how we combine these methods, we do appreciate the ECSS philosophy, but we really discard most of the documentation. The only thing we write down is at the top level of the satellite. So we have the mission requirements and we have the major interface requirements. But after that, there's no change on the subsystem developer. If he complies with the top level interfaces, he can do pretty much whatever he likes. So this allows room for innovation, and also it reduces the effort to actually maintain this documentation, because if you start writing documentation, you need to update it and update it. But if you maintain the design such that it contains the documentation itself, then your documentation is always up to date. So we aim to use development tools that allow us to actually integrate the documentation into the design. We are not conducting any ECSS type reviews, but we understand the need for them. So we replace them with these Scrum type meetings. So we have weekly meetings reporting progress and discussing possible problems, finding solutions for them. One aspect is also that the whole ISI team is working in the same office, 50 square meters. And there's 15 of us, so it's quite crowded, but also the communication is always instant. You don't have to email someone or try to see if someone is there. You see in a second if someone is there, if you can go talk to him. There's a picture, there's, I would say, 10 workstations in this area, so it's a bit crowded, but it works if you're not easily distracted, let's put it this way. So some other design choices, using COTS components is probably not a big surprise. We want to do low-cost stuff. One interesting thing is that we actually use a lot of CubeSat subsystems. So there are a lot of CubeSat subsystem providers in the market right now. So we're actually buying those subsystems and putting them into our microsatellite. We try to minimize the need for in-house testing, so we try to find component lists. We really put a lot of effort in doing this research to find component lists on possible flight components. We're aiming for a 400-kilometer orbit. Well, as you heard in the previous presentation, the orbital life is not too high there, so we actually are going to include some form of propulsion in the satellite. This 400-kilometer orbit is good for one reason that, well, at least one reason. The radiation environment is pretty tolerable there. That's one reason why the International Space Station is there, because you cannot put humans in the radiation environment. We like to prototype a lot, so at the open office we have these prototypes lying around. Everyone can grab a subsystem, see how it fits to another subsystem, and it's really, I think it's fun and useful to do this. And also we are doing the interfacing testing all the time. We don't believe in an integration phase, we rather integrate all the time. In the software engineering we have adopted these Texas Instruments tools for developing automotive grade software. So we aim to achieve this kind of reliability. Version control, GitHub is a good example of a tool which allows you to document things without actually writing documentation. So you always have your previous versions and old code available. We're using a very lightweight operating system in the onboard computer, so this is also something that's used very much in the embedded industry, so we have a lot of support for that. And again, when we write code, we try to make it so that actually you can read it almost like a text. So we try to mask everything that's low level or explain it very well in the code. And the ECS standard for the telecommand packet utilization is one big element while we're writing the software. Looking at how the satellite looks from inside, our onboard computer actually is used only to execute telecommands, schedule telecommands, and to collect telemetry from the satellite. We actually then have distributed logic, for example, in the payload. All the radar processing and this kind of stuff is done independently in the instrument, and it also has its own downlink radio. So the OBC software design is not too complicated. We are using CAN bus for the spacecraft data bus because we have heard a lot of problems with I2C, which is the other CubeSat industry standard. We are now building the hardware for the onboard computer, and we are writing the software at the same time. And every time we get a new hardware, we port the software to that one, and then continue developing with that. So that way we can continuously integrate the software to new environment. And already we started component level qualification with the available prototypes, which have let's say 90% of the flight components. For example, we went to Jyväskylä lab to do radiation testing with 60 megaelectron-volt protons. So we bombarded the electronics up to 25 K-rad. So we got a nice single event offset and total liners in those tests. These protons are too weak to test for latch-ups, so we will just include overcurrent protection to everywhere. But we saw a lot of bit flips. We could characterize our components, and we saw the radiation tolerance also. Thermal qualification, this is nothing special. We have this thermal chamber. We can test components when we get them. They work. So on the hardware side, we currently have the second prototype version, but the third prototype will actually be already represented in the flight model. So the only change will be to change in the flight connectors. The software is not so done yet because we still have a lot of interfacing to do with some other less ready subsystems. And so the next version of the onboard computer will be representative of most likely the flight model of the computer. So what we have learned so far, you definitely need the mission requirements. We have dumped a lot of documentation, but you cannot dump the mission requirements. But if you don't specify every low-level requirement, you allow some flexibility and some room for innovation. When you have these Scrum-like meetings, you have to be able to assign people to other tasks if you notice that some task is lagging behind or there's too many people doing something. We like to prototype, at least I like to prototype. It's fun, and it's actually useful when you see how things fit together. In our team, we like to have people who continuously can expand their areas of expertise. They are not content being good at something. They want to be better, always better in something more. And if you work with maybe a bit more traditional organization, you might notice that things don't work always that fast. So you should take that into account. So especially our own university has been a good teacher in this bureaucracy. So in conclusion, we are aiming for a ice monitoring satellite constellation. And the process we are using to develop this is aiming to extract the maximum contribution. And we read a lot of ECS standards, but we are not implementing them to the letter. But you can still definitely see the influence in the OBC design. Thank you.
Thank you, Mr. Nielsen. Please, your questions?
So it sounds like such a perfect working environment. Is there any students left for all the one development?
Well, that's actually a big problem right now in the laboratory, but we are helping as much as we can. So Jan tries to get us to work alongside Aalto.
I don't need microphone. I have a question about this I2C. You said you had problems about I2C, and I went over to CAN, but CAN has even higher overhead than I2C. Can you elaborate on that?
Yes, so this I2C problems, we have heard from many CubeSats, they have stuck I2C drivers, and we know that CAN is being used actually in ESA missions. It has an easy as a standard for CAN bus usage, so we have more trust in the CAN bus. And we don't consider the overhead too much, especially we have the Texas Instruments tools to actually create the driver code for CAN bus. So for us, it's not that much of overhead.
Also, less than one problems with I2C in until more.
Development or in flight?
Can you say a few words about propulsion and you're talking about the constellation, how you would spread it out and what is the requirements on the mission, how strict you need to maintain the constellation?
How precise constellation we can achieve affects directly how good refresh rate we can achieve. So if we achieve the optimal constellation, we can achieve like 3-hour refresh rate on any Arctic location. But with less accurate constellation, it might be 6 hours, 12 hours. And I think current satellite systems offer something like 24 hours, 48 hours. So we need to do better than that to offer something new. And about the propulsion, we are looking at a small ion thruster. So we have selected the thruster, but the pressure management system and the tanks are still in development.
Last question. One question. Thank you. And the next presenter, Riccardo Mantellato from University of Padua, CISAS Giuseppe Colombo.
Hello everybody, I'm Riccardo. I am from Padua, Italy, and I'm here to present you a new mission concept we are working on in last month, involving tether and docking that are through our solid backgrounds in Padua. So the name of the project is TED. Tethered electromagnetic docking. So I'm going to explain first the concept. So the concept of the tethered electromagnetic docking is principally is a docking system, a cooperative docking system, and with that, we can do the docking maneuver in 2 steps. The first one is called soft docking and involves a magnetic probe with which we can do the sub-alignment using electromagnetic forces and a leash probe shot from the chaser. And the second one, the hard docking, the mechanical hard docking. After that is winded. To better explain this, I made a graphical example, very easy, very simple. So, like every rendezvous maneuver, we start with our course rendezvous. So the distance between chaser and target is to be defined, but it's on the order of tens of meters. Okay. Up to 100 meters. And after we have the rendezvous, with attitude control, we control the pointing of our launch system, and we shoot. What happens if we shoot wrong? Nothing, we can retry it. We just rewind the tether, repoint the trigger, and then shoot again. If you do a nice shoot, the magnetic self-alignment of the probe. Here, for example, we have a ferromagnetic probe, and on the target there is a small ferromagnetic, a small electromagnet. Okay, so once the probe is close to the target, there are electromagnetic forces that self-align the probe with the target. And this is called soft docking. After the stabilization phase of the target and chaser, there is the rewinding of the tether that take the target into physical contact with the chaser. And then we have the hard docking. And the dock maneuver is finished. So the traditional docking system some drawbacks. For example, they experience high load transmission between target and chaser. They need very high precision during close navigation, and they need very strict alignment. With that concept, we have very low impact forces because the only impact is that between the probe and the target. We need very looser attitude and navigation control, and we have the magnetic self-alignment. In particular, about attitude control, with the tether electromagnetic docking, we need only a coarse relative attitude control stabilization, let's say some degrees. And about the navigation, the tether do all the hard job. I mean, once the soft docking user realized, the tether is rewinded, and the navigation between the chaser and the target is aided by the tether. So, what are the advantages of that concept? There is a disruptive degrees of docking maneuver time that now are very low. It's more safe, it's safer. There is a lower demand of resources, power, guidance, navigation control, attitude control, and in the end, we can enable docking between microsats or even CubeSats, who knows. In Padua, there is a student team now working on the dropper thesis campaign that involves a very early concept of launch system and docking target, and they are going to launch it in November, I think. So, and their primary objective is to study the dynamic of self-aligning magnetic docking. So they launch a probe, they study the dynamic of the tether and the dynamic response to the target here. So let's go fishing. The guys from Fel's team have made this. Where is the mouse? I made this very short movie to better explain the concept. So now here we have the smaller satellite is the chaser, and the bigger one is the target. So we start with rendezvous and the launch of the probe. Here we have self-aligning magnetic soft docking. Okay, the stabilization phase is a little bit exaggerated. I want to point it out again that we are talking, for now, we are talking about cooperative docking system, that is, target and chaser are communicating. And then after the rewinding of the data is finished, we can have the hard docking, the mechanical, physical docking. And it's done. So we outlined the mission objectives. We try to keep it very easy because it will be our first CubeSat. So we would like to have a very easy mission to start, and it will be a demonstration mission, technology demonstration mission. The statement of the mission is to demonstrate the feasibility and the effectiveness of tether-shot docking outside in space. The two objectives are to demonstrate the knowledge of technology and to validate the launch system and the retrievable rail system. About the procedure, I will talk later. We'll pass here. Okay, here a brief, very brief mission overview. So we have first of all we want to deploy from the CubeSat mother satellite a target. We want to deploy it and keep it physically connected throughout all the mission. So, and we want the target to be at least at 20 centimeters from the mother satellite. Of course, we want the deployment to be low distances, and it must allow the unfolding of the deployment system during the tether rewind. This is FEL's launch system, and we plan to use the same technology. It's very simple technology. It involves spring and some guides here to shoot the probe the more aligned with the vertical as possible. Okay, here on test concept we have electromagnetic probe, and it is leashed to the mother satellite, and it is powered through the tether. The launch system must be rechargeable and provides proper guides to allow several cycles. Okay, I will not talk in deep about tether and electrical relay system. I would like to tell you that there is no spacing heritage for bipolar wires. Only one pole wire are being tested in space. The tether must provide electrical power to the probe, must be sufficiently stiff along the longitudinal axis, but enough low stiffness for lateral bending. And of course must have proper isolation properties for thermal and electrical point of view. About the retrievable rail system, there are some missions that use a retrievable tether deployer. For example, the TSS-1 in the early 90s. And recently there is a Japanese mission that flowed a retrievable rail system, but up to now we didn't get any result from that mission. So there is insufficient experience in space for a real tether deployer. And it must be frictionless, low inertia, must be, of course, retrievable. That will guarantee, of course, also the multi-shot capability, and must be very, very high reliable. About the bus, I don't have nothing to tell special, because we are going to use standard structure. We're going to use solar panels, a communication system, and normal command and data engine, and overall attitude control, passive attitude control, because for this experiment we don't need a particular attitude control and determination. About the orbit and the attitude of satellites, we expect to launch in a LEO orbit, high inclination orbit. We're gonna use 3 hysteresis rods to passively down angular velocity. 1 rods along each axis. Early simulation have shown that with this kind of attitude control, passive control, we can dump initial angular velocity. Here, 10, and 15 degrees per second. We can dump it down to 0.15 degrees per second in 1 day. And for us, it is sufficient because we just need the CubeSat not to roll very fast, just to launch and retrieve the tether, and very fast compared to the period of the velocity rate. Mission activities. Okay, after the satellite is put on orbit, we have the tumbling, the tumbling of the CubeSat with the hysteresis rods, and then the experiment can start. So again, the target is deployed. The target is a ferromagnetic plate here. Then we want to launch the electromagnetic probe. Is soft up with the target. The tether is winded. The launch system is recharged, and a new cycle is ready to begin. So we want to perform this test as much possible, as many times as possible, to have statistical results. So about the future work, as I said at the beginning, in Padua we have a solid background in tether and docking system, mechanical docking system. And about the magnetic alignment, there's the guys from the first experiment that are going to test it in Bremen at the Zalm Tower. Our docking, we already flew in Baxus some years ago. A new, hard docking for Microsoft, and it was successful. And about the tether, we have strong background from SETS 1 and SETS 2 NASA mission, and overall from BET's FP7 program. And about the retrievable array system, we have to develop it, and we intend to submit a Rexus proposal for next year. So we want to build it and send it with the Rexus mission next year, I think. And okay, apart from this, we are open to international collaboration, because apart the technology part, we are new. We never launch a satellite, a CubeSat. So, for example, ground station, project management, launch, procurement, all that stuff. We are new, so we are ready to learn, and again, we are open to international collaboration. And thank you.
Thank you, Ricardo. Any questions?
Thanks. Just a quick question. What the tether is made of? I'm sorry if I didn't catch it.
The tether is conducting tether. Here we outlined 3 possible configurations. I didn't explain that. We have the coaxial one, we have the twisted one, and we have the commercial off-the-shelf one. We hope to use this. This is a thicker configuration, but it's also the cheapest and the most ready. Thanks.
Did you consider using electrostatic attachment instead of magnetic attachment?
Yes, we did, and we also the team from docking and capture San Francisco is studying the electrostatic capture. I think it's called like that. And but until now, we prefer the electromagnetic one because it's stronger and good kilovolts generator on CubeSat must be challenging. But the electrostatic solution will be very useful for capturing, not only soft docking. I mean, for capturing, for example, physically. It's very interesting, and we thought about that, but we want to start with this one.
Last question.
Maybe at the presentation, but what kind of distances are you considering? How far away from can you dock? And also, have you estimated sort of what kind of power requirements does the system pose? Because you need quite a bit of electric power to power the electromagnet to keep the tether from detaching the target.
Yeah, you mean the CubeSat mission, or in general?
In general.
In general, no, we didn't. For the CubeSat, first experiment is using 10 watts electromagnetic, and it's very strong. And we thought to use 1.5 electromagnetic for CubeSat. For general uses, it depends. It depends a lot from dimensions of the satellites.
Have you had any thoughts about the distance?
Yes.
Like 2 meters, 10 meters, 100 meters?
Yeah, in the order of tens of meters. So let's say 50, 70.
Thank you. Sorry, discussion can be continued during coffee break. Thank you, Pietro. And the next presenter is Pietro Motta from University of Catania. Please, the floor is yours.
Hi everyone, I'm Pietro Motta from the University of Catania in the south of Italy, in Sicily, one of the oldest universities in Italy. This topic is a collaboration, has been developed within the project Synergy. This is a collaboration with the University of Catania and other companies. And the main objective of this Synergy project is to develop a control and recording data about a network of energy production and consumption. The contents of this presentation will be smart metering, because it is the main topic of this project, Synergy, and I will explain what is it, why I'm talking about it, current and proposed architecture, characteristics of the probable nanosatellite, a case study to understand the situation, and at last an overview of satellite versus mobile architecture. Smart metering, as you say, is a device that can record the production and consumption of energy, and usually they are in a hub to record and are connected with the provider of the service, usually for electricity, but also for gas and water. In the smart metering system, we have sophisticated devices with a lot of new applications that did consist also in the possibility to send the information recorded to on other devices, for example, central station or business analysis center, and the center can answer and command the smart metering and manage the network and put off some product or customer. The smart metering, we are talking about it, we are working in University of Catania about it because there is this directive of the European Parliament that say that in the whole member state, all the meters have to be smart if you are putting a new one or you are substitution of the old one, and if the benefits are enough, if you don't, the costs are not greater than the benefits. Okay, this is the current architecture in development in the world. You can see. Okay, you can see 3 meters, for example, the most common, electricity, gas, water, and all the meters data are condensed in only one packet or only one frame, and then collected by a gateway, a keeper. The keeper takes for several customers, several users, and it transmits. This is its purpose, to transmit with the network, usually with mobile, and the network can operate and choose decision and answer to the gateway, which can act accordingly, for example, shutting down some meter or changing some parameters. This is the proposed architecture we have with a satellite. It's all the same, but it changes the medium of the transmission. Of course, the network devices are the same. It changes only gateway, the keeper, a little bit because it doesn't communicate with the GPRS or mobile system now, but with non-satellite, so it's a little bit different. The benefits we think are economic because we can cover density, high density areas with less devices structure, only one non-satellite. If you want to cover extremely huge areas, you have to build with mobile network a radio base station, repeaters, and so on. And the communication network management and implementation probably could be lower. The coverage is variable from medium to extremely wide, as I say, and depending on the distance, you can choose it, of course. About infrastructure, the coverage of rural or particular areas not covered by other systems, because there are a lot of places in the world not covered by the mobile system or other kind of system, and you can cover with a satellite easily. And facilities and this get over some problem of digital divide. The characteristic of nanosatellite in this concept, everyone has to be defined because we are only in the early stage of definition for this mission. We are at the first attempt with the nanosatellite. It's our fifth time. So we have to define everything, but we are talking about low levels of LEO because we don't need to cover so huge areas, because if you cover so much area, you need a huge data rate, or the coverage time will be minutes, the diameter can be chosen, the transmission frequency has to be defined, and only one thing we know is the cost as low as possible, because to be competitive with a stable mobile network, we have to be cheap. There are also constraints, other consideration to do. Data rate, because more customer means more data rate or more satellite. Less customer is less data rate, but less saving money. And this is a proposal for commercial mission, so we have to be competitive, economically competitive. Over the decade, because we have to think something about maintain the orbit, because also for an economic question we need a lifetime mission as long as possible. We created at least 3 years to be competitive with the mobile system. Reliability for the same reason, so we need less failures, instrument degradation, longer satellite lifetime, and redundancy. We have to think also of backup devices and backup satellite to avoid the total system collapse, because if you send only a nanosatellite to cover all the, for example, to cover a region and the satellite have a failure or crash, you will lose everything and you are not covered at all for years probably. So this is a case of study. It's only an example to understand what we're thinking, and we are considering my region, Sicily, in the very south of Italy, almost Africa. We have 5 million of inhabitants, and so we are considering all 5 million because, okay, there are families, but there are also commercial activity and considering electricity, water, gas, number of gateway, 1 gateway for 100 users, so 58,000. We suppose 5 kilobits per day are included and an altitude of 400 kilometers, and we want to cover 500 kilometers because it's enough. The number of orbits will be circa 15, 16, and we consider 14 orbits plus 1 or 2 backup orbits for emergency. The coverage period around 6 by 7, and the throughput is quite big, 28 megabits per second, but we are talking about 5 million people. It's quite a huge number. Here we can see and analyze about millions of customers, cost for 1 year, varying the number of the customers. For example, we are considering that one satellite can cover at maximum 5 billion customers. It's our supposed. One SIM fee, it means 1 gateway fee per month. It's 40 cents for each gateway, and we are supposed cost of not so much, it's 150,000 euros. You can see here that initially with a low number of user customer, it's not competitive. The mobile network is cheaper, but with a large number of users, the distance of money is quite a lot. We are saving a lot of money, and for some provider of the service could be a good thing, I think. And we can see this part. It seems it's not convenient because you have, for example, only 1 million people or less, and you say, why I have to put in orbit one nanosatellite? I can put a radio base or some radio base. But if you think in a condition like the middle of the city, okay, here, for example, there are a lot of places not covered for mobile systems. So you can guess that if you have a power plant or something else, petrol factory, and you wanna be in contact daily with him, it could be a good idea, another satellite. For example, another example is this one. For example, you are in the desert in Iraq, and you have a huge plant, and you have to contact it. So you are in the desert, you don't have so many users, and you can use all the throughput for less users, some power plants, and you can read the data more time per day. I forget that for the directive, European directive, you must read the data from each smart meter twice per day. At least twice. You can use more for this, and you can daily control or hour per hour control your plant. Okay, maybe in Iraq you have other problems for kamikaze or something like that, but we cannot solve it. And at least we can see is a very optimistic view. 5 years mission. For example, we sent 2 nanosatellites, one of backup, and they live for 5 years. For example, one for 2 years, and the next one turn on. And you can see that with the same number before, the total SIM cost per year is 240,000 euros. That is less of our price, but only for 1 year. If we reach a lifetime of 2 years, we are already cheaper. And if we imagine 5-year cost, it's a lot of difference. 1 million with 300. We can close with a compare table. Cost, so we saw cost for connectivity, mobile, satellite. We saw if we have enough long life, it's a good idea to choose satellite. The potential uptime is underride the mobile system because you can reach, with the mobile system, you will reach your customers in every time you want. The satellite, you have to wait the orbit. Fixed network independence, this is our benefit because we don't need a radio base station, we don't need cable, we don't need anything. Also some satellite and a gateway. Current implementability, it's good. It's a benefit of mobile because the mobile is a stable option, already tested and used, and our is not because we have to test, we have to develop, we have to make some research. It's a big challenge. And for large broadcasting and multicasting, for example, it's easy to broadcast with a satellite. We can update all the gateway together, or we can change the firmware or ask for some emergency situation for catastrophe. And at this end, it's a big challenge, but we think it's possible in the future. Thank you.
Yeah, I have a couple of questions here. It's an interesting study. I might have not caught what you said. So each terminal will get the data from the satellite as well?
Not each terminal, but each gateway.
Each gateway, okay.
Yeah, we suppose it. Where is it? Okay. Right.
So,
Here. We supposed one gateway for each user.
Yeah. But the gateway is basically a satellite station with tracking.
It is almost a satellite station.
So
Yeah.
how much? The
But-
cost of that is a couple thousand euros, right?
Yeah, but that's why it's a big challenge, and we are talking about the future, because there is also this problem to consider. And but some new prototype of nanosatellite with the hybrid rate, we think that okay, they use 5 meters antenna on the ground, so it's. But probably we are studying for the future, for our future, and we are.
Yeah, I have another comment. Okay, if you do not need to downlink data and you only need to uplink, then what you should also have in your column is a comparison with existing systems like Global Star or there are a couple other, Turaya, Iridium, and so on. Because for Global Star you can get a terminal for simplex link for very short message, which costs nothing, like less than €1. And your application has low data rates, and that's the benefit of that system is that it's already deployed, and you pay.
Yeah, but yes, of course, but we are talking also to transmit in both way.
Yeah.
So because you can ask something to the decision system support DSS, for example, or the DSS has something to say to some customers. For example, if you don't pay your budget, they can switch off your smart meter.
But having enough power on a nano satellite to reach to the ground.
That's another thing to be defined. That's why we are talking about future, and I say it's a big challenge. But really, I don't know if it will be possible, and we will carry out it, but we are starting to think about it.
Are the prices for mobile calculated using hardware only, or is it basically the end price for the consumer? So
No, it's not for the consumer. For example, most weeks we asked it for these offers for a big company. If you buy, for example, 5,000 SIMs, we give you this special price, and the price was higher. It was 50 cents, but we want to consider less to see if really we are competitive with this solution or not.
Okay, and does it basically include personnel costs and also operators?
No, I think that the personnel is not included, so you have to put more, and it's not included for both the infrastructure cost, for example, magnetism, because we consider that are quite the same in both. You have to put the gateway or whatever, for example.
I have actually two questions. First is, have you analyzed the issue with collisions? You have tens of thousands, if not millions, stations sending simultaneously. This is one question. And second is related. How this comparison looks like if you take into account the frequency allocation fees?
We still didn't do this consideration very well, but for the first one we did a generic consideration. We need a new or a good protocol with very fast establishing of the connection and avoid the collision. Yes, we are in the early stage. We're not considering the in-deep, but we are thinking about it. It's another big challenge. It's all a group of big challenges.
Okay, thank you, Pietro. I think this discussion of challenges can be continued during coffee break. And now the last presentation, Mr. Paul Lias, Company Space.
Hello, my name is Paulias. Today I will speak to you about new CubeSat structure and Hayes family, which is designed from TSTC, which is a spin-off company from the SQ project. So, by 2020, more than 1,000 satellites, nanosatellites, will be launched to orbit. But the current problem is that most of the missions will fail because of mechanical failures, and because of that, most of the small CubeSats will be just space debris, and we want to solve this problem because we want that all satellites will look like that and will be really successful missions. So today I will speak about PS space, but it is exactly about design and development for nanosatellites, and also about products and testing. So PS Space, as I mentioned before, is a spin-off company from SQ, and our members were the first ones who started in the project, so they have a lot of experience in development. Last year, in November, we started the company. Since back then, we have always been working on these new products. Our vision is, of course, not only to go to space, but also to sell our products here on Earth to the wider market. Today, we are supported by Vega Fund, which was founded by Tartu University and the SEB Bank to help new spin-off companies from the university to start. So, what are our products exactly? We have a family of CubeSat structures, solar panel deployment system, and antenna deployment system. Later, I will speak more about these products. And we have also services which will be interesting for you, as I saw, at least for some of you here in the public. We have also development services, so you will give us requirements what you will exactly need. And we will basically develop all the mechanical drawings for interfaces for manufacturing, and also the CAD models. And if needed, we can do also all the special prototyping for custom-made satellites and rapid prototyping. And as Andres told yesterday that Paul will probably not speak about this group, then I thought about that, and it was a really good idea actually to speak about this group, because everything we make here is based on S-Group knowledge, and every single screw will be selected with help of the S-Group results actually. So let's go. Let's go back to history, where I started. And as you see, here is the first CAD model actually we made for S-Cube. Here's the last one. Here's the first prototype we made for S-Cube, and here is the satellite before launch. And of course, not everything went that good we expected and we wanted. And for example, as you can see, the structure from S-Cube was made out from one piece of aluminium. Here in the beginning, it looked like a really good idea that it's really easy, all the tolerances will be correct, and we will have less problems. But here, if you wanted to integrate the whole system, we saw here before the laughing there that it wasn't that good. That it would be much better to have a structure which contains more components, and it's easier to integrate the whole system. So then we were searching for a new solution for our product. And of course, the product development, most of the people think that it begins everything here in CAD. That we just take the computer and we start drawing. This is completely wrong. At first, we have to do some basic sketches, thousands of them, just pencil and paper, just weeks of it. And then we continue with prototyping. Here you can see the first prototype for the antenna deployment system, SQ. As you can see, it's a really student style, without any funding. After we have finished the first test, that you see that, okay, it's working, then you should take the computer, you should make the first drawings out of which components to use. Then you will get back to the testing, how the modifications will work. And if you see that, okay, this design will work, then you will go to manufacturing, because the real manufacturing costs so much to play around. If it's manufactured, then we will go to testing, and if the testing results are positive, we have the product ready. So now let's go to the first product. It's our useless structure family, and the first prototype of it is already here. We will have CubeSats from 1 unit until 12 unit CubeSats. And as we learned from S-Cube that not every screw is good for space use. Therefore, we will use only materials which will be non-ferromagnetic. And our customers can self-decide which screws they will order. And also the same is for coatings, because depending on the orbit or mission, not every color is good. Here for the prototype, we look of course red, because red is something really beautiful. And in case of S-Cube, we used not the same material as said in the CubeSat specification, but we used basically similar material. And why we use it is because it's much easier to get it in Europe, but the material is actually the same. So it's just engineering. There's no difference in engineering, but just the difference in cost and time. So it's much easier, much more efficient. Here, the structure will be, it's quite easy to integrate because it's divided into, for example, this 2-unit CubeSat into 2 stacks. And also you can put the stacks in any direction basically you need. So here is the CAD models of those satellites from small to big. In the next future we will have already everything manufactured, because this here on this 2-unit CubeSat we will try to find all the mistakes out before manufacturing the larger ones. So, but I think it's time to go back in time. Antenna deployment system. So it looked like in S-Cube. Here was the first design of the antenna deployment system. Here is the last design assembled already. Here are the pictures I showed you before. So really basic design, just to get some making tests. And we had very different solutions. And actually the last solution we took, it was a small box from aluminium milled out in one piece. It was, in case of S-Cube, the design was quite good, but there could have been some modifications in the end, but the problem is that we can't sell it. It's too custom. It's only for S-Cube, and as we saw, there are many limitations, so we searched for something else. And therefore, our idea was that to put the satellite antennas inside the satellite, it would take too much space. So we understood that we have to mount them on the sides and mount them this way, that we have more space inside the spacecraft, and also to use all the space we have on the side, for example, solar panels. We will use for the antennas the same material as for S-Cube 1. They will be profiled iridium copper antennas, which will work as springs. And also the making mechanism for the deployments will be reusable, so you can test it as much as you want, basically, without changing any components. And it's possible to use this system from starting 1 unit CubeSat. So now we can't go back in time anymore, because the solar panel deployment system, we didn't have such a thing on S-Cube 1, as you remember. The solar panel deployment system will be possible to use with 90 and 135 degrees. And it will have also a launch lock to fix the panels during launch. basically the design for it is already ready, but because of some difficulties, I don't want to show you because it's our product and it's somehow optimizing stuff. So hopefully if you want to buy it, you will see it, but not today. Yeah, so it's sort of it's a business secret how it will look like. And of course, the solar deployment system will use the same melting mechanisms as an antenna deployment system, and it has some similarities to some S-Cube deployable systems. And also in DLR, similar systems are used, so it's kind of safe. And hopefully, these panels will be also used for some next questions. So testing is the most interesting part actually, because most of the teams forget about testing, and before the test you have to prepare a lot, and there was actually many stories in this vibration testing, and I think you will see, if you see this movie, you will see a lot about that, or maybe not. And in testing times, you had to design many things for testing overnight, and all the designing process and manufacturing, we didn't have enough time, so many mistakes came inside. Now, for our products, we have much more time to prepare for it, and currently we are also working on the testing fixtures and other equipment to not waste money because of some engineering mistakes, and we are trying to investigate a lot to have not only these products I showed you before, but also to have testing services and also equipment for testing for other student missions who don't have that much time to prepare testing equipment. And here you can see some actually pictures I didn't show that not that many people have seen. Here's a picture where some parts were made really in the beginning of January during S-Cube testing. And I was really watching at my clock that, 30 minutes back I had to be in some facility and the testing should be already in progress. So yeah, here is it. So thank you for your attention, and if you are interested, then please you can follow us on Facebook, Twitter, and also on our web page, which will hopefully update also in some time with some more information about our products. And if you have any questions, you can ask or send it per email or ask per Skype. So, please.
Thank you, Paul. Any questions?
I didn't look to the recent CubeSat specifications, but the aluminum type you use, I think it's not according to CubeSat standard.
It's said that those others are allowed. It's basically the same. It's not written that you have to use this 6061, but also other materials. And as we saw it from S-Cube before, so the basic. So in this case, it doesn't make sense actually to use in Europe this 6061. So we had already in S-Cube, we tried to make S-Cube grain from the right material, but we saw that if you want to order it in Europe, you will pay a lot more for this material, and the delivery times will be much longer. And then we saw that the other material is basically the same. You will get it over one basically next day, and and works. So in the case of economics and engineering, it makes more sense to use this material.
More questions? Probably everybody would ask questions at coffee cup. So thank you, Paul.